Okay, fourth video on Solo's mechanisms, resource efficiency and the production function. Assume an economy with 10 people on an island and 10 trees per week wash up on the beach. Okay, so we've got households and a production arena. I'll draw the factory, but of course actually we've got the beach. And I guess these 10 people are going to head off to work. That's L is 10. And then we've got some exogenous R is also 10, right? Per week. So our time unit is per week. Okie doke. Furthermore, the islanders have a technology called knives, which allows them to cut the trees into planks, which can be rapidly made into houses. Okay, but it's a technology called knives, but we don't model knives as a capital good which actually have to be manufactured. Okay, so we've dropped capital, we just have this resource flow, the labor flow, and the flow of product. And the product conveniently is houses, given this picture, and they make 0.01 houses per week, 10 workers, 10 trees per week. What do they need more of to boost their rate of house building? Okay, so the idea here is that you think intuitively about these numbers. Okay, so the answer is not mathematically here in the question. You need to use your brain and think intuitively. So this is 1/100th of a house. 10 trees are making 1/100th of a house. So for a whole house, that would be 1,000 trees. Okay, that seems like an awful lot. So it seems like these trees are actually, there's way more trees than they can use given their knife technology. Okay, they're cutting up the trees with knives. 10 of them are washing up on the beach a week. There's only 10 people. Clearly they're not able to use all of these trees. Okay, so if we imagine these being completely in excess supply, then we can drop them from the production function because they're not limiting. So then we could have a production function which was y equals AL L. Okay? But y is 0.01 and L is 10. So that tells us that AL must be, let me think here, 0.01 equals AL times 10. So AL is 0.01. And what are the units of that? So Y is houses per week, L is workers, so AL must have units, houses per week per worker, or houses per worker per week. Okay, right, but so far so good. We've got a value for AL, but now we want to actually bring back AR, and we want a CES function. What value should we have for epsilon? Or maybe I'm doing things in the wrong order here. checking my notes. Okay. How substitutable are workers and trees? Like, yeah, it's tricky. How do I explain this? I'm trying to think, how do I explain this in the past? Basically, they're not very substitutable, right? We've already got way too many trees that we, more trees than we can use. If we add even more trees, like what's going to happen to house production? Absolutely nothing. Okay, but if we had the opposite situation with not enough trees and loads of workers, how much would it help with more workers? Not at all. So the substitutability should be low, which means that epsilon should be negative. Okay. Cobb-Douglas is like pretty good substitutability. Elasticity 1. Okay. Epsilon not 0, that's Cobb-Douglas. That's pretty good substitutability. Epsilon 1, that's perfect substitutability. Epsilon goes towards minus infinity, that's no substitutability for Leontief. So we might think there's not much substitutability in this case. If we want to make it really simple, we could say epsilon is minus 1. And then we'd have this. Because then that makes things super simple. So what do they need more of to boost their rate of house building? They need more workers. Suggest values for elasticity of substitution between the inputs and knowledge levels. Okay, right. We worked out AL, 0.01 houses per worker per week. We worked out a value for epsilon, or we sort of made up a value, which was minus 1. Then the elasticity of substitution, we could call that eta, is 1 over 1 minus epsilon. 1 minus minus 1 is 1 plus 1, that's 2. So that would be a half. The elasticity of substitution would be a half. Remember, Cobb-Douglas is 1. But what about AR? So, imagine instead that labor is in excess supply and trees are super short. Then we could simplify the production function like this. Okay, we've got more workers than we can use, they're just hanging around. So this is very large, we can just drop it and we have ARR to the minus 1 to the minus 1, it's just ARR. Y is houses per week. R is trees per week. So what's AR? It's houses per tree, right? That's the units of AR. So how many houses can you get out of a tree? Well, it depends on the house and it depends on the trees, right? You can make up what you like. But we could maybe say 0.1, say 0.1 houses per tree. So with 10 trees you can build a house. Seems reasonable to me if it's a pretty small house and reasonably big trees. So something like that would make sense for AR. Okay? So AL is 0.01, AR is 0.1, and elasticity substitution is a half, or epsilon is minus 1. Would be reasonable numbers to choose. Okay. Now assume that the islanders invent a technology called sawmills. And again, we assume over time they've got the capital goods, they've built the sawmill. What do they need more of now in order to boost their rate of house building? Suggests new values for the knowledge levels. Okay, so now clearly they've got plenty of time in a week to cut up 10 trees into planks, given that they've got a sawmill instead of knives. So clearly AL, their labor productivity, has gone up hugely. Labor productivity was houses per worker per week given unlimited trees. So with a sawmill, that might be, and remember we told that they can quickly turn planks into houses, so that takes no time at all. The tricky bit is cutting the planks. So they're obviously very simple houses, these. Okay, so if you've got a sawmill, how many houses could you make per worker per week? Well, who knows? But if we say that it's 10, so if AL was 10, but AR, well, it might change. We'll talk about that in class. We have a think about that, what might happen to AR. But let's hold it the same for now. 0.1, sorry. AR is 0.1. L and R are still 10, so now we would have Y is ALL, so AL is now 10, so that's 1 over 100. ARR is 1 over 0.1 times 10 is 1 to the minus 1. So that's effectively, it's going to be very close to 1. Yeah, Y is 1. We make 1 house per week because we've got 10 trees washing up. Labor is in excess supply. We've got loads of labor, but you need 10 trees per house minimum. That's what we said here. Before, it was the other way round. I never went through that, but we had Y is ALL. AL we said was 0.01 times L was 0.1. Oh, did I get that right? No. AL should have been 0.001, right? I think. I think I got that wrong, right? Because Y is 0.01. L is 10. So ALL should be 0.01. Divide by 10. AL is 0.001. I don't know what I said earlier, but it was wrong. AL should be 0.001 initially. So ALL is 0.01 to the minus 1. So we got 1 over that plus ARR, we said AR was 0.1 times 10 is 1 all to the minus 1. This is 100 plus 1 to the minus 1. It's 101. 1 over 101, which is roughly 0.01. Yeah. Okay. So that's just an exercise in trying to get your head around how these functions work, what these productivity levels mean. Think about the units, think about the physical interpretation of what is going on, right? Don't just do the math, think about what you're doing and what it means. Okay, and that even in the more mathematical questions, because then I want you to be able to link this then to discussing things about the real world. So you need to understand the model in its own terms, but then to be able to link it to discussions about the real world. That's a huge aim of the course, right? Okay, end of this video.